So today we're going to look at oxidation reduction reactions, often called, because oxidation reduction is so many syllables, it's often called redox reactions. There's a lot of types of reactions that fit in this category, but basically what it is it's a transfer of electron from one to another. I've written one type, but let's look at just a simple. If A sends an electron to B, that would be an oxidation reduction reaction. A would now become positively charged, B becomes negatively charged. But so we can see this kind of, sometimes it's a formal transfer of an electron like that. Sometimes it's just an effective transfer of an electron. So let's get into it and how we can track these and recognize oxidation reduction reactions. Here is one. If I take a piece of solid magnesium, which is an active metal, and I drop it into a beaker of hydrochloric acid, it's fizzing away. Turn it so you can see. So it's fizzing away, and so the reaction is a very vigorous one because I've got the strong enough acid, and now it's gone, right? So the magnesium disappeared. So I've got the hydrochloric acid here. Let's look at the net ionic equation. So let's break this up. Hydrochloric acid is a strong acid. So 2H plus 2Cl minus. And here, let's break this aqueous up. Magnesium is 2 plus ion in this magnesium chloride solution. And Cl2, there are 2 chloride ions separate in the solution. Chloride is my spectator. So let's write the net ionic, because a lot of times for redox reactions, the net ionic just is a little cleaner and it makes it more clear what's happening. Magnesium reacts with the hydrogen ions in the solution to become a positive ion. Neutral metals do not dissolve in water. Metal ions do dissolve in water. Aqueous. And then the bubbles we saw was the hydrogen gas being formed. There's a transfer of electrons occurring here. Magnesium was neutral. It had all of its electrons. It sends its 2 valence electrons to these positive hydrogen ions. Now the hydrogen ions are neutral and they escape the gas. So the transfer of electrons is an oxidation reduction reaction. We say that magnesium loses electrons, and we call that oxidized. That's just the name that was given. A lot of these reactions involve oxygen, so we say it was oxidized. If it loses electrons, we call it oxidized. It went from a neutral state to a positive ion. H plus gains electrons, and that's being called reduced. Remember that, and it's something you have to know. Okay, that's oxidation, losing electron. Gaining electrons is reduced. You say, wait, if you're gaining while reduced, you're gaining a negative charge, right? Which always flips things. The other way that people use to remember it, oil rig. Oxidation is loss. Losing electrons is oxidation. Gaining electrons, reduction is gain. So that's a way to remember it. These kinds of things. So this would be a reaction involving magnesium being oxidized. That's one kind by an acid. I can also, I don't have this as a demo, but if I put solid magnesium in a solution that contains an ion, for example, copper 2 ion, that has a more of affinity for electrons than magnesium. The magnesium will actually give its valence electrons to copper because magnesium is the more active metal. And so in the process, magnesium now is the positive ion. Copper becomes the neutral atom or neutral material. So the transfer of electrons from magnesium to copper, magnesium loses electrons. It is oxidized. The copper 2 ions gain those electrons. It is reduced. So sometimes this transfer is very obvious and okay, I can see where the electrons went. They actually transferred. Sometimes they're within covalent compounds. It's not as obvious, so we need a set of rules to figure out what's being oxidized, what's being reduced, and to recognize when it's an oxidation reduction reaction. So let's look at what these rules are basically. And the first one is, so we're going to have a set of rules. If it's an element, one. If it's an element, neutral element, just, it's oxygen gas, it's magnesium solid, right? It's, it could be any number of forms, but if it's a neutral element, its oxidation number, I'm just going to put ox number, is 0. We say it has an oxidation state of 0. 2, monatomic ion. These first two are the easy ones, right? The easy one. If it's a monatomic ion, it's the chloride ion. The oxidation number or the oxidation state is the charge of the ion. Chloride has a charge of 1. Its oxidation state is -1. If I have this compound, FeCl3, iron can have, it's a transition metal, it can have more than one oxidation state. I've got 3 chlorides, each with a -1 charge. What is the charge of iron in this place? It's got a +3 charge. If it's a monatomic ion, like this, the charge of the ion is the oxidation state. And this one, iron 3 chloride, iron has a +3 oxidation state. Iron, of course, can also, it's a transition metal, it can have more than one. In this one, this is iron 2 chloride because the iron has a +2 oxidation state. Now, what about those? So that's more clear. Ionic compounds, it's a little more clear. What about, let's go to rule 3. And later on in the course, we'll get into all the whys of this. For right now, let's just know the rules. Rule 3, nonmetals bonded to nonmetals. Whoops. Covalent bonds. Right, so what about nonmetal? You look for 3 things. A, does it have oxygen? Is oxygen in the mix? For example, look at something like nitrogen dioxide. Because oxygen is a big electron puller, if oxygen is bonded to some other nonmetal, in general, almost always, it would have a -2 oxidation state. It's an electron puller. We'll get into more details as to why, but for right now, just know the rule. -2. Because this is a neutral, nitrogen dioxide neutral compound, the oxidation states must add up to be neutral. So we say it has a +4 oxidation state. Note that without doing the full Lewis, this is a covalent, neutral, covalently bonded compound. Those are not charges. It doesn't mean the nitrogen has a +4 charge. Oxygen does not have a -2 charge. It's just in this arrangement, we're giving the oxygen a -2 oxidation state. It's a bookkeeping situation, so just to keep track of where the electrons are going, who's got more of the electrons than the other. There's an exception, so usually oxygen has a -2 in most all compounds. The exceptions that do come up are peroxides. In this case, because oxygen is bonded to another oxygen, neither one is pulling more. In peroxides, oxygen has a -1 oxidation state. And then, of course, oxygen, if it's just the neutral oxygen element, that's an oxidation state of 0. So when we're looking at nonmetals bonded to nonmetals, first thing to look for, is there oxygen in that compound? Use this rule first. Second, rule B. Does it have hydrogen? If yes, Hydrogen and metals. Those are hydrides, for example, calcium hydride. In that case, the hydrogen gets a -1 oxidation state. Calcium, of course, is a +2. When it's bonded with metals, these are not as common. If it's H and non-metals, much more common. The hydrogen gets a +1 oxidation state. So in a compound like CH4, I've got 4 hydrogens, give them each a +1 state, and then carbon is going to have a -4 oxidation state. Again, covalent compound. Those are not the charges. They're simply these things called oxidation states where we can keep track of who is sharing the electrons, or is it changing its arrangement to something where it has less share of those electrons. And of course, H2 as a neutral element would have an oxidation state of 0. So, does it have oxygen first? Second, is there hydrogen in the mix? Use this, hydrogen and metals. It's -1. Hydrogen with nonmetals, +1. Third rule, look for halogens. Does it have fluorine, chlorine, bromine, iodine in it? Halogens usually would get a -1. Right there on that last one, they usually tend to add 1 electron. However, with oxygen, the exception is fluorine, because fluorine's always -1 and when it's bonded to anything other than itself. When it's bonded with oxygen, for example, let's use the ion ClO2 minus, the chlorite ion. Chlorine, so we say usually it's -1, but wait, it's bonded to oxygen. Who wins? Oxygen wins. Give oxygen the -2 state. Here's chlorine. The net of this is a polyatomic ion. The net is -1, so this whole arrangement has to have the oxidation numbers come to -1 +3, right? +3 and -4 gives you a net of -1. So this is remember the polyatomic ion, chlorine bonded to 2 oxygens covalently. They've added an electron to have a negative charge, but in this case, we're giving them these oxidation states. So we can use these then to look at, and let's just do one, and then we'll of course practice with some more. So for example, we can use these rules and say, okay, if I have this in a reaction like this, sodium chloride in solution, and I'm going to mix it with bromine, what will happen is the chloride was Cl minus, right? Oxidation state of -1. The bromine was neutral, it was 0. Here, the bromine becomes -1, and the chlorine is now 0. So I would say, okay, what happened to chlorine? It went from -1 to 0. -1 to 0. Lost an electron. Losing electron, Cl is oxidized. What about bromine? It went from 0 to -1. That's adding an electron is reduced. So first we start and we look at the reaction. We assign the oxidation numbers throughout the reaction, and then we go through and figure out who's got oxidized, who got reduced.